Grand finale. Gordana Matic is closing it out for us. Gordana is telling us about filtering the Heegaard Floer contact invariant.
So thank you for letting me speak. I don't know about this grand finale, but as a I have to turn this on. Okay. Since I'm the last speaker, it's up to me to thank all the organizers for a wonderful conference. Thank you all, and thank you for inviting me. I'm going to talk about the refinement on the contact invariant of in Heegaard Floer homology contact invariant of Ozat and Szabo. So as Josh said, I'm going to be filtering the contact invariant. Of course, it doesn't make sense, but you'll see what I mean. This is joint work with Cagatay Kutluhan, Jeremy Van Horn Morris, and Andy Wand. So all the questions I don't know how to answer, you should ask Andy. So this is the contact invariant in Heegaard Floer homology, and well, we've just heard a definition of what's a contact structure. So let M be a three-manifold and Xi a contact structure. Then Ozat and Szabo defined the contact invariant in Heegaard Floer as an element in Heegaard Floer homology of minus M, and this we've heard from John about similar things in a different flavor of Heegaard Floer homology, and I'm going to be talking about a different flavor of Floer homology. I'm going to be talking about Heegaard Floer homology, and so I first want to say just a couple of properties of this invariant. So as in the case of the instanton invariant, C of Xi is 0 if Xi is overtwisted. And maybe I will say what it means for Xi to be overtwisted. That means that there is a Legendrian curve, so a curve where the contact planes, so Xi is a plane distribution, which is a kernel of some alpha, where alpha wedge d alpha is positive, and where we have a Legendrian curve L bounding a disk. So that would be called an overtwisted disk, and we are going to say that the contact invariant, that the contact structure is tight if it doesn't contain such an overtwisted disk. So let me get rid of that. So on the other hand, as John said, a contact invariant is non-zero if Xi is Stein fillable. And it would be nice to be able to say something about Xi which is just tight, which means not overtwisted. And so the question, when this invariant was first defined, it was hoping that it would recognize the tightness of a contact structure, but that is not true. Oops, I'm too short for that.
There's a hook.
Is there?
Over far right.
All the way on the right.
Uh-huh. I have never done this clearly. In my department, we have a little rope that's hanging. It works good for me. The answer is, of course, that C of psi is 0 for some tight manifold. So in particular, there is a notion of Giroux torsion, which means that if there is inside of the 3 manifold, there is an embedded torus, which has a neighborhood in which the contact planes make a full twist as per going out from the neighborhood. When there is a Giroux torsion, then we also have C of psi equals 0, and so there is work of many people, but in particular Gugini, maybe the final touch was done by Gugini, Honda, and Jeremy Van Hoy Morris. Who proved that if psi contains Giroux torsion, then C of psi is also 0. There are many other manifolds, many other sort of manifolds with boundary that also ensure existence of Giroux torsion, and so there were some generalizations to many other so manifolds with convex boundary. That generalize from, on one hand, the neighborhood of an overtwisted disk, which means that manifold is overtwisted, a neighborhood of a torus with a full twist, which is the Giroux torsion. And so there are other things, for example, taking a neighborhood of a convex surface with some dividing set that is of a particular shape, that it has some separating property, and then taking an S1 invariant piece is going to produce also the sort of fake Giroux torsion. Wendell talks about planar torsion. And so there are various obstructions to C of psi being non-zero, which are, you know, what kind of piece of a manifold you have to have a contact invariant vanish. So we would like to figure out some way to kind of measure what kind of twisting pieces are in this invariant, are in this contact manifold that makes C of psi equal 0. So this is what our refinement is partially about. So Lachev and Wendell defined something that was attempting to measure this kind of planar torsion, which they called an algebraic torsion, or order of algebraic torsion. Which was defined in contact homology, which is a vastly more complicated object than a Heegaard Floer homology, and relying on a very precise understanding of pseudo-holomorphic curves in the simplexization and so on. So, and it's not very computable in principle. And so, in the paper they wrote I forget now, a few years ago, there is an appendix by Hutchings that reinterprets their definition of algebraic torsion in terms of ECH. So the embedded contact homology, which is a lot simpler object than the contact homology, and it is this interpretation in terms of ECH and theorems of Cohen, Gigini, Honda, and Kutluhan, Lee, Taubes that say that ECH kind of mirrors HF in its various guises, in particular HF hat, that gave us the idea to go and look for filtration on HF hat in terms of the data that we get from the contact structure. So let me state the main theorem. And so from this data, we can cook up the invariant. So there is invariant of contact manifold and psi, taking values in Z non-negative union to infinity, which is so such that we kind of spread the difference between 0 and non-zero in the Heegaard Floer invariant. And so first of all, so we call the invariant the spectral order. And we denote it by O of psi. And so first of all, O of psi is 0 if psi is overtwisted. Second, should say what happens in the case of Stein fillable. O of psi is infinity if psi is Stein fillable. So more specifically, O of psi is non-decreasing under Legendrian surgery. So John was mentioning Legendrian surgery as a way of obtaining Stein manifolds and contact structures. So if you take, so what he was talking was, if you take B3 and the standard contact structure on S3 and you add along Legendrian knots these handles with a particular framing coming from the Legendrian framing -1, then what you obtain is a new contact manifold. So it's a new manifold determined by the knot and the new contact structure. So you can do this even when you don't start with S3. So you can start with any manifold with a contact structure and with some Legendrian link, and you can add handles along that Legendrian link, or in particular Legendrian knots to start with, and get a new manifold and build what is called a Stein cobordism. And what our construction, our invariant satisfies is that the O of psi prime is going to be bigger than or equal than O of psi. So In particular, from a definition, it will be pretty clear that O of the standard contact structure on S3 is infinity, and so any Stein fillable contact structure will also have a contact invariant infinity. So now, of course, the natural question might be, is there anything in between 0 and infinity? And so in order to be able to do that, we need to be able to calculate these invariants in some case, at least, when we can get a handle of what is true. Well, we can do better than that. We have this property that O of psi is calculable, giving enough time and patience, or strong enough computers. Is calculable from any open book description of psi. Okay, so given that we can calculate this, we did certain examples, so we know that O of psi takes on infinitely many different values. And I'm going to give a set of particular examples that does that. And so, in particular, it will also be an infinite sequence of examples where we have obstruction to Stein cobordism between any two of those existence of Stein cobordism between pairs where this inequality is violated. So. Yes.
Can you compute it from nice value?
Yeah. I mean, you have so I'm going to say what exactly this has to be. What we have to do. We have to take multi-pointed nice diagrams, right? But yeah. So clearly, the question is there something that we found which is tight and O of psi is 0? And the answer is no. So there is this, wish that we have and hope that we have that this will be an invariant that will actually recognize tightness. And there is a work of Andy's that is geometric characterization in terms of the open book of tightness, and we're hoping to be able to translate it into this, but we're not there. So, the talk should say theorems, definitions, examples. So there are some more theorems, but I'll leave it for now and think about this as our main theorem. And so I should now go to the definition. Heegaard Floer homology is defined from using a Heegaard decomposition of a 3-manifold, and in case that manifold comes equipped with a contact structure, there are some particularly nice preferred Heegaard decompositions, and in those preferred Heegaard decompositions, there is a preferred generator of H hat that is the Oswald-Sabel contact invariant. So we want to look at that. So I'm going to remind you of what that is. So if M psi is a contact manifold, then Giroux gives us sort of a Giroux correspondence between isotopic classes of contact manifolds and stabilization and open book decompositions up to positive stabilizations. So M psi by Giroux gives us an open book decomposition. So what's an open book decomposition? So it's a, we should say it's a surface with self-diffeomorphism where phi restricted to the boundary. So this is a surface with boundary, phi restricted to the boundary is the identity, and my M is diffeomorphic to S cross 0, 1 mod an equivalence class induced by phi, where what is this equivalence class? I take so let me draw S as planar, because then I can draw a real picture. So I have S cross I, and phi is some diffeomorphism of the surface fixing the boundary, and my equivalence class, my equivalence relation is that x1 is equivalent to phi of x 0 for every x in S, and that xt is equivalent to xs for every s and t when x is in the boundary of S. So as we saw John do it, I'm going to glue this up to itself, and then I'm going to squash all the boundary cylinders down to a point. So I can think of this as now I want to think of the Heegaard decomposition that comes from this. What I want to do is I want to cut this into two pieces, going from 0 to a half and from a half to 1. And each piece, when I squish the boundary, clearly becomes a corresponding handle body. And so I have two handle bodies, one corresponding to S cross 0 a half, and the other corresponding to S cross a half to 1. And they get identified so that the top gets glued to the bottom. Okay, so we want to talk about the compressing disks, and we see in this picture the compressing disks showing up in the obvious way, and the way to do it is to choose a set of arcs. I think I just I want to choose a set of arcs that I'm going to call A1, A2 that cut my surface into a disk. So I take those arcs AI cross the interval 0, 1 half, and that gives me a disk di, and the boundary of di are the boundaries of the compressing disks. Alpha I for the first handle body, and then what I want to do is so if I do that on the bottom half, I want to take a little push off of the AI curves to get BIs, and then look at the corresponding disks for the top handle body, and that's going to give me a Heegaard decomposition. So a Heegaard, not just a Heegaard decomposition, but a Heegaard diagram. And this diagram has a special property. So if I draw it, so this certainly is obvious in this planar picture, but it is true for any surface. So in general, I'm going to have a surface my page of the book, open book, will be some surface with some genus and some multiple boundary components, and I will take a set of compressing arcs and push them off a little bit. And think of this as happening on the level, the common level as 1/2, and then the Heegaard diagram, the common boundary of the two handle bodies is S1/2 union minus S0, which is identified with S. 1, and I wanna, so the boundary of the red disks is just a symmetric copy of AI's, and then the boundary of the blue disks on S0 are depending on phi or monodromy. So this is going to give us some Heegaard diagram representing our 3-manifold. And so Ozak and Szabo from a Heegaard diagram define a chain complex, CH hat. In this chain complex, the chain groups are spanned over whatever we work over. I'm going to work over S2, over Z mod 2, and they're spanned by what we say intersection points between T alpha and T beta, where, what do I mean by T alpha and T beta? T alpha is a product of alpha curves. T beta is a product of beta curves in the symmetric product of the surface sigma. And so each one of these guys corresponds to a tuple, x1 through xg, or whatever, however many components. This may not be g, but however many components of the boundary and so on we have, how many we need to cut the surface down to a disk, with the property that every xi lives on some curve alpha I intersect with beta j, where beta j depends on I by some permutation. So my x has one point from each alpha and each beta curve. So there is one obvious point like that, which is the one unique point that lives on S1/2, and we call that generator xi, and it's a fact that the homology class of this generator in HS hat is the contact invariant. Okay, so well, I only said what the chains are. I didn't say what the boundary maps are. And the boundary maps come from of some x is a sum over all y's and over all homotopy classes from x to y with certain index condition, and we count some number of points in a moduli space and then multiply by x, and we use that to define the boundary operator, and that gives us a Heegaard Floer homology, and also in Szabo showed that it's independent of all the choices that you make, and so on. It's pretty easy to see that the contact invariant is 0 for the overtwisted contact structure, because if there is an overtwisted contact structure, then we know that we can find an open book decomposition in which we can find a set of arcs that cut it to make a Heegaard diagram, so that one of the arcs comes right back and gives us element that kills in the homology, the contact class. So, okay, so when contact structure is overtwisted, there is an obvious disk that kills the contact invariant, and that disk is just a simple disk with two points on the end, a simple holomorphic disk. And what we want to do is we want to somehow use the fact that this disk sometimes doesn't exist, certainly not obviously in the case when the contact structure is not overtwisted, to kind of filter this boundary map, in fact. So let me give a definition. So we're going to make we're going to split this boundary operator according to how complicated the domain that we're counting in the boundary operator is. So what are we counting here? What we're counting are these maps phi. So in pi 2 from x to y. So what we think of is these points x and y that live in this symmetric product. In that symmetric product, there are these half-dimensional subspaces, T alpha and T beta, and we're counting the number of pseudo-holomorphic disks in a particular almost complex structure that we can vary that take a standard disk, so that they take the left part of it to the beta curve, the right part of it to the alpha curve, and they miss some set of base points. And I forgot to say that in the definition of Heegaard Floer homology, we put a base point here, and we're counting only the things, in the simplest case of the Heegaard Floer, the simplest version, we're counting only the things that miss this. And so this lives in the symmetric product of sigma, and the way we can interpret it to see what it has to do with our Heegaard diagram is that we can take some branch cover of this disk, and there is a map from that branch cover where, we have marked the portions that are supposed to go to alpha and beta, and that branch cover has a map to our sigma, and those domains are what is represented by pi 2 of xy. So these branch covers are surfaces with some number of with the number of arcs, pairs of points in them, and we're looking at a map. And so what we want to identify is how complicated these branch covers can be. So this is very rough, but I needed to say that. So there are these domains. The image inside of sigma is a domain D with puncture or with boundaries on alpha curves and beta curves. And when we have such a domain, represents a map in the boundary of x, relating x to y, we are going to see it as living inside of sigma in such a way that the boundary of domain as say restricted to alpha curves connects x to y. So if this contributes to that sum, it's going to be represented as a domain that connects point x to point y along alpha and beta curves in this picture. So what we want to do is define an integer associated to it. And so it is going to be the filtration level of that corresponding to this domain in the boundary map. So we're going to, following Michael Hutchins, define j plus of d, interpret it properly in this situation to be calculable from the sort of the local properties of the domain and from seeing how the domain is constructed. So we can just look at these domains and calculate this so for people that know what I mean by nx and ny, it's okay if you don't, I don't have time to explain. So we have twice these local coefficients at the x and y for our domain, minus 1, which is for the Maslow index, and then plus these correction terms where this absolute value of x is equal to the number of cycles in this permutation that corresponds to x. Okay? So every generator corresponds to some permutation where this we say that the sigma is identity for our generator x psi. So we number alpha 1 through alpha n our arcs, and so our contact generator psi is an identity, and it has, you know, however many arcs we had, that many cycles. And so for each one of them, we count the number of cycles, and this can be reinterpreted to also say that this is equal to the Maslow index minus twice the Euler number plus x minus y. And there are other interpretations that is not hard to show that this is really an even number. Okay. Okay. So with that in mind, and in some gluing properties, we can now break down our boundary map so we now have our boundary map, boundary 0, boundary 1, boundary 2, and for any x, this is going to be finite. So it breaks down into finite limited case, I'd like. So if we now think about what happens in the Heegaard Floer complex, our boundary map in the Heegaard Floer gets split up into pieces, and in order to take care of that, we augment our a basic complex. We take again following Michael Hutchins, CF of so sigma, alpha, beta, and there's this base point. So I want to say this all can be done by adding more curves. So if we add more curves, we have to add more base points. So we have multi-pointed diagrams, and we do exactly the same. So these alpha and betas could be bigger than alpha being just a basis. And so we're going to tensor this now. This is CF hat of sigma alpha beta z tensored with ftt minus 1. So basically what we have are infinitely many copies of this original chain complex, except now in vertical direction we just think about delta 0, and then delta 1, and delta 2, and so on. And so we have this complex that's invariant under translation in this direction, but I've managed to break up my differential, and we can introduce now filtration on this complex by taking only the coefficients up to t to power k, and then this boundary map is respects the filtration, so we can get a spectral sequence, and we define our O of say sigma, alpha, beta, z, and of course we're taking some almost complex structure with respect to which we're working, and we are defining this to be the smallest k such that the class of x psi dies on the k plus first page of the spectral sequence. Okay, so if things are very simple and we find a unique y, say, that kills the contact invariant, and we figure out what its j plus is, and we know that there is nothing else coming out of that element, and we have a simple situation like that, then we can read this off very simply from just that picture. If the situation is more complicated, I mean, we actually have to calculate further, but in principle, certainly, given a particular open book and arcs alphas and betas and so on, this is calculable. So, of course, the question is, how about the choices that we made here? And you know what? So, first of all, of course, there is a shock, because here is an example. So I can take a contact manifold that's given by an open book, which is 3 times punctured disk, with the monodromy given by the Dane twist. So let's say +1 +1 +1 and -2. And if we take some bases and cut this up and draw a picture, we can actually find unique j plus equals 2 domain. So it would suggest that O of this psi is 1. On the other hand, we can easily see that this represents an overtwisted contact structure, so it can't be that we can actually read something off of a basis. So, of course, when Michael Hutchin defined his invariant, it was also not invariant under all the choices, so the way to get around it is to say take a minimum over all the choices, except then you can't calculate everything, right? So, but psi is overtwisted. So we had to think harder. We couldn't just take the basis. And we realized that what at least we have to take is what we call a full set of arcs, which decomposes our surface into triangles. And then it turned out that we actually have to take more, that for every boundary component, we need to take an extra arc. So this is one for this boundary component, say one for this boundary component, one for this boundary component, one for this boundary component. And if we take that many arcs, and we take a multi-pointed Heegaard diagram corresponding to such frame, that it actually realizes the O of psi, which is the minimum of O of sigma alpha beta multi-pointed potentially Z and J over all choices of the surface and the phi. I should have said S and phi, and all alphas that contain a basis, and that we can actually calculate the minimum by looking at just one open book with a complicated enough set of arcs. So I promised examples, so so here is our set of examples that we managed to do the calculations for. So given k bigger than or equal than 2 and m bigger than k, and taking again 3 times punctured disk with the monodromy k positive Dane twist around each boundary component, and then negative m twist around a belt curve like that. We had the manifold Km and the contact structure on it, Km, and we can give bounds to this O. We know that O has to be less than or equal than K and bigger than or equal than K minus 5. When K is bigger than 6, this gives us lower bound away from 0. And when K is less than or equal than 5, we still have that O of M, Km, psi Km is bigger than 0. So these contact structures have contact invariant 0. And so to see that the contact invariant 0, one can use the capping disks argument of John Baldwin and see that things become overtwisted. And so the contact structure is 0. Contact invariant is 0. On the other hand, this is tight by work of Kawamura and Ito, and the examples show up in the work of Conway, Kalati, and Kulkarni as some of the examples on planar surfaces where that they analyze there, where they find that you can destroy they talk about this in terms of surgery on a transverse knot in a contact structure. So so maybe I should show you the domain in this picture. So you know, our calculation is an analysis of the situation. So certainly to get an upper bound, we just need to find the domain. To get a lower bound is a lot more complicated argument. We haven't really gotten ourselves to the point where we can plug this into the program that will calculate it. We have to modify some existing program that will calculate here for homology to get more calculation. Also, let me just to point out how complicated these calculations become. If I just take this basis, in this basis, the domain that you can find. So there is no disks that you can find in this picture. This is even more complicated than the picture I drew before, where I said we couldn't find the disk. So we have, say I'm going to draw the picture for k equals 2 and m equals 3, which is the simplest one that we have. So this is for that arc, and then for this arc we have I did something wrong. I should have gone out here. Sorry. There is the left twisting. And our domain has the following multiplicity, has this thing with multiplicity 2, this thing with multiplicity 1. So the y that's going to map to this is our x1, x2 is our contact invariant, and x3 we're going to have up there on top, having it fixed. And so our domain is this. I'm drawing the boundary of the domain. So I go to 0 over here, so this is the boundary. It's going to close up here. And then there is another boundary component, which is this. So here's our domain with multiplicities 2, 2, 2, 1, 1, 0. See, this is 1, 1, 1, 1, 0. So when we go and calculate J plus from that formula over there, this is clearly a domain, and it is it has J plus equal to 4. So we get that O of psi is less than or equal than 2. And if you have more twists, you get comparatively more complicated domain, but with exactly the same pattern. And you know, here, so it's easy, not so hard to find the domain, and it's a lot easier to prove there aren't any other ones. Or that whatever they could possibly exist has to have J plus high enough. So we don't prove they're the only ones. We kind of have a limit on how complicated the domains are, which gives us the inequality. So now, of course, I didn't talk about invariance under homotopies of arcs. If we want to make this diagram nice, we have to push things in, and the things break up, and in a nice diagram, all domains are going to have J plus equal either 2 or 0. But the point is that in that that picture that I have, that we now have a chain of things that kill each other, and that chain sort of pushes you to actually have a longer distance between the filtered element that kills the contact invariant and the contact invariant, and it preserves whatever it needs to preserve. So I guess I'll stop here.
Do you do any computation which are not just presenting something with a convenient diagram?
We don't have any like triangle inequality or, triangle surgery triangle or something. So the only calculations we have are really hands-on arguments. So that, better calculational tools are certainly needed. And, I should say that, there are directions you can take this in, and certainly there's an obvious generalization to sutured manifolds and the contact invariant in the sutured manifold. And Andras Juhas, and a student of his, whose last name I think is Kang, had done a calculation for a Giroux twist domain, showing that if there is a Giroux twist, then this invariant is less than or equal than 2, sorry. So, of course, if you have some piece of your manifold that you understand, then you can complete it to an open book of the whole manifold, and you're finding domains killing a contact invariant in certain J, then that is going to persist. The upper bound is going to persist. So we see the inclusion will, like honor the order, right? So if you have an overtwisted disk in a manifold, then the order will be 0. If you have a piece in a manifold with a small order, then that will kind of push your order down in general. So, for example, we also have a theorem that says that the order of a connected sum is the minimum of the 2 orders. So it tells you if you take in particular, if you take like a Stein fillable manifold and something that has finite order, and you take a connect sum, you get something that has finite order, and therefore it's not Stein fillable, which, one can also parlay that into sort of the monoids of monoids in the group of automorphisms, where you define them by bounding the order, and so just like sort of soup up everything that you can do with in standard worlds too. And let's thank the organizers once again. This is now. Yes.